Now, in this series, I've argued up here, you see that I've argued the existence of the universe implies God's existence. Objective morality requires God's existence. Free will and free thought require God's existence. Last week I argued that the origin of life implies God's existence. Now, some of you I know will be pleased to know that this is the last class in this series. Next week, Andy Baker is going to be speaking during the Bible class, and then the week after that, we'll come back to something more typical. But in this morning's class, my contention is it's more reasonable to believe that purposeless natural processes are not sufficient to explain the alleged transformation of the first cell into every organism that has ever existed on earth than to believe that they are. And it is more reasonable to believe that the diversity of life requires intelligent input than to believe it does not. Now, according to the atheistic, the naturalistic scenario, after the first cell arose, came into being spontaneously in the wild from non-living matter, all forms of life that have ever existed descended from that first cell through blind, undirected processes. Now, more specifically, the standard claim is that natural selection, acting on random mutations of DNA, random changes to those nucleotide sequences in DNA, natural selection acting on that gradually over many generations morphed the first cell into the mind-boggling array of radically different organisms. Now, all the new innovations in the history of life allegedly were produced by this process. Now, this is modern Western culture's creation story. That's what this is, which has, to a large extent, displaced the biblical narrative. This is now our creation story, that naturally we had a cell arise, and that over many, many generations, through random mutation and natural selection, it produced the vast array of organisms that have lived on the planet. Though allowance is made for contributions from some other less important undirected processes, random mutation and natural selection are accepted as the driving force of diversification. This is neo-Darwinism. When you see that term, that's what it is. Darwin didn't know what's producing variations. Now the idea is the variations are produced by mutations of the DNA of this order of these nucleotide bases. Now, this claim has major problems. It's not the kind of thing that they will tell you, certainly at lower levels of science teaching, but it has major problems. Our current knowledge suggests that there's not enough time under any atheistic scenario for the large number of different proteins present in those countless life forms to have been generated, let alone to have been integrated into functioning systems without some kind of intelligent input, without some kind of programming. The Cambridge-educated philosopher of science, Stephen Meyer, he noted in a presentation he gave in 2018 at Biola University, Meyer said, I don't know what's happening there, but Meyer said, major figures in evolutionary biology are now expressing profound doubts precisely about the creative power of the mutation natural selection mechanism, the alleged cause of the major biological change over the history of life. So this is something that is being recognized and admitted by people. There was a conference in November of 2016 that was hosted by the Royal Society of London. Now, the Royal Society of London is the oldest scientific body in the world. It was founded in 1660. And there was a conference held there, and that conference was called by leading evolutionary theorists, largely to address the adequacy of neo-Darwinian orthodoxy for explaining the major innovations in the history of life. This is why this was called, and as Meyer states, it's kind of like a test, I guess. As Meyer says, he says, many of these theorists have acknowledged in their own scientific writings that the mutation natural selection mechanism lacks creative power. It explains the small-scale variations very well. It doesn't explain where major new forms of life come from. It explains the minor changes in the shape and size of the finch beaks, but it doesn't explain where birds come from in the first place. For example, one of the evolutionary theorists involved in calling this conference was the Austrian evolutionary biologist Gerd Müller, who in fact, he opened the conference. He gave the initial talk at the conference, and he had previously written with his co-author, a cell biologist, Stuart Newman. He had written, he says, the neo-Darwinian paradigm still represents the central explanatory framework of evolution as exemplified by recent textbooks. So this is neo-Darwinian orthodoxy. You have random mutation and natural selection. He says, this refined and canonical theory concerns the variational dynamics and adaptation of existing forms. It is a gene-centered, gradualistic, and externalistic theory according to which all evolutionary modification is a result of external selection acting on incremental genetic variation, random variation of the DNA, the nucleotide sequences. He says the resulting adaptations lead to successive replacement of phenotypes, these observable characteristics and traits. That's what a phenotype is. Replacement of phenotypes and hence to evolution. He says, although this theory can account for the phenomena it concentrates on, namely variation of traits in populations, it completely avoids the origination of phenotypic traits and of organismal form. In other words, neo-Darwinism has no theory of the generative. Now, this is an evolutionary biologist. This isn't me. This isn't a preacher. This is a leading evolutionary theorist who's saying it has no theory of the generative. As a consequence, current evolutionary theory can predict what will be maintained, but not what will appear. What is still lacking is an evolutionary theory that specifically addresses the morphological aspects, the body form aspects of evolution, and integrates the interactional epigenetic aspects with the genetic. Now, the 2016 conference was titled New Trends in Evolutionary Biology. And in his opening talk at that conference, Gerd Müller, he outlined what he called, quote, the explanatory deficits of neo-Darwinism, including the inability to explain the, quote, origin of phenotypic complexity and, quote, the origin of phenotypic novelties. Now, that's a pretty big shortfall for a theory that says, I'm going to tell you how from a single cell you got a whale and a potato and everything else. That's a pretty large thing. Now, one of the problems is that to change one organism into a fundamentally different organism requires the creation of many new and different types of cells. If you're going to go up in levels of complexity, you're going to have to generate many new and different types of cells. Functionally more complex animals, they require more cell types to perform their more diverse functions. There must be cells that are dedicated to specific functions in higher order organisms. Different cell types are organized to form tissues. Different tissues are organized to form organs. Different organs are organized to form systems and high-level body plans. Just as an example, Sponges have 5 cell types. Flatworms have 20 cell types. You have the arthropods have 50 cell types. Humans have hundreds of cell types. For example, stem cells, red blood cells, various types of white blood cells, nerve cells, various types of muscle cells, cartilage cells, various types of bone cells, skin cells, fat cells, sex cells, and on and on. We have all kinds of different cell types. And remember that proteins, they are the workhorses of cells. They are the building material of the cell, and they perform all kinds of functions within the cell. Each new cell type requires the production of new and specialized proteins to build and to service the cell. So all right, let me see where I was here. All right, so you have those types of cells. So that in turn, see, if you have new cell types, and then you have to have new cell types which require new proteins to do that, well, that in turn then requires the instructions for manufacturing those specific proteins. You have to then have the instructions. If I need new proteins, I then have to have the instructions for those new proteins coded in the DNA. So I have to have this sequence that you have, these nucleotide bases, has to be changed so they now will give you the code for manufacturing those proteins. Okay? So you need new proteins. Now you're going to have to change the DNA so it will code to manufacture those proteins. So they have to get rearranged into the new sequences to have those instructions. As Meyer says, the epithelial cell, just to give you one specific cell type, the epithelial cell lining a gut or intestine, for example, secretes a specific digestive enzyme. This enzyme requires structural proteins to modify its shape and regulatory enzymes to control the secretion of the digestive enzyme itself. Thus, building novel cell types typically requires building novel proteins, which requires assembly instructions for building proteins, that is, genetic information. Thus, an increase in the number of cell types implies an increase in the amount of genetic information. All right, so why is that a problem? The problem is that randomly changing, I hope some of this from last week you'll remember, the problem is that randomly changing the nucleotide sequence, which you have to do to instruct and to code for the new proteins that you're going to need. Randomly doing that, changing that sequence is necessary to build those required proteins. Randomness has no chance of doing it. It has no chance of doing it. The odds against randomly hitting, just randomly varying the nucleotide sequence that would code for only just one new protein, of only 100 amino acids long, it's prohibitively low. I explained last week the probability of randomly arranging. Remember, you have 20 amino acids that are used in living things. Proteins are made up of amino acids. You have 20 kinds like that. And the probability of randomly arranging the 20 different amino acids used in living things into a specific sequence of only 100 amino acids, a protein of only 100 amino acids, a specific sequence here, the improbability is 1 in 10 to the 130th power. That's 1 over 1 followed by 130 zeros. It's insane. As Meyer says in this slide that I ran over last week, I rushed over it, but Meyer points out that the probability calculation of the arranging the nucleotide sequence on the DNA, on this side, the nucleotides in the DNA, and arranging the amino acid sequence on the protein, that those things are roughly equivalent. Okay, so for simplicity's sake, the calculation is typically made off of the probability of arranging the amino acids in the protein sequence. Now, because some amino acids can substitute, okay, I said you have to have these things in the right order. Well, that's true, but it's not exact. There's redundancy built in, and you can have some amino acids you could have different ones. So let's say we have a chain of 100 amino acids. Slot 2 might take amino acid 5, 8, and 9. Slot 12, you might be able to substitute some. So what Doug Axe did, who has a doctorate in chemical engineering from Caltech, he calculated and estimated how frequently can you change those amino acid sequences, substitute them, so that it doesn't have to be exact, it's got some play. And that then reduced the probability, right? Obviously, if I can make some substitutions, it's not going to have to be quite as exact. So when he calculated those, he came to the conclusion that to get a protein of 100 amino acids, the improbability is 1 over 10 to the 65th power. Now that's a lot smaller. I mean, 10 to the 65th is way less than 10 to the 130th. Okay, but it's still insanely improbable. Because as I said last week, it's estimated that there are only 10 to the 65th atoms in the galaxy. Okay, so we're talking about something like that. It's a ridiculous improbability. Now you say, well, okay, I understand those are really long odds. I get that. But even so, if you rolled the nucleotide dice enough times, well, then you're going to cut into that improbability, and at some point, after enough rolls, it's actually going to become likely, right? I mean, Meyer's example that he used, so let's say you have a bicycle lock that has 4 dials on it, and the total number of possible combinations is 10,000. Okay, so if a thief sits down and has the time, and he can randomly sample out of that 10,000 possibilities, he can randomly sample over 5,000 of them. Well, now it becomes likely that he's going to stumble on the correct combination because he has sampled more than half of the space. You have 10,000 possible combinations. If I sample more than 5,000 of those possibilities, now it's more likely than not that in doing so, I'm going to land on the combination. Okay, so that may be what you're thinking. You say, all right, I see that this is a huge improbability, but if you throw the dice enough times, that huge improbability becomes something that is likely. But the problem is that the improbability of randomly stumbling onto the right nucleotide combination for a new protein of only 100 amino acids, it's so great that there's not enough time to make enough attempts to throw the dice to overcome the vast odds against it. You say, well, how do you even get a handle on something like that? Well, I'm glad you asked that, because based on work by scientists at the University of Georgia, work by scientists there, it's calculated, or it's an estimate obviously, but that the total number of individual organisms, I'm not talking about species, I'm talking about individual organisms that have ever lived, is 10 to the 40th power, ever lived on the earth. So that's the estimate. You say, well, the overwhelming majority of those were bacteria. I mean, you would understand that, right? They're bacteria. They statistically swamp all other life forms in terms of numbers. They statistically swamp them because of their vast population size and their short generation time. So when we're thinking about all of the individual organisms, the number of individual organisms that have ever lived on Earth, 10 to the 40th, of which the vast majority are bacteria. Now, if you make the exceedingly generous assumption that every organism that ever lived inherited a new, randomly generated 300 nucleotide sequence, right? That would be a sequence large enough to code for a protein of 100 amino acids. If you remember from last week, these nucleotide sequences, they code in triplets. So for 100 amino acids, I would need a nucleotide basis 300 of them. So if you assume that every one of those organisms had a randomly generated 300 nucleotide sequence, well then each organism that ever lived had one roll of the dice to land on this sequence of nucleotide bases to create a protein of 100 amino acids. But if you make that assumption, you're still what? You still have 10 to the 40th chances, and that leaves you with an improbability of landing on the right sequence. The probability then is still only 1 out of 10 to the 25th. You see, so you wind up like this. You have 10 to the 40th, you assume 300 nucleotide sequence per organism, thus one new potential gene of the necessary length. Therefore, 10 to the 40th attempts at a new gene, throws of the dice, but you wind up still with your odds being 1 out of 10 to the 25th, which is that number that I've typed there. That's a big number. That's like winning the lottery a few times. Okay, and that's just for one, that's for one gene to code for one protein of only 100 amino acids. So I want you to see that in changing these body forms, the new cell types clearly require, you're going to have to generate a lot of new proteins out here. And to do that randomly is a major, major problem. You know, so you say, well, most of them are bacteria, so why do you think it's a generous assumption to think that only one roll of the dice? Well, mutations don't pop up all the time. They've studied bacteria a lot. And the average mutation rate is you only get one mutation anywhere in a bacterial genome per 330 cell replications per generation. Per genome, per generation. And Richard Linsky's work, he's done generations and generations, decades of work with E. coli. And their mutation rate is only 1 out of 1,000. Generations or cell replications anywhere in the genome. So it's being very generous, because if I said, look, all right, you're going to replicate this bacteria 330 times before you would expect one mutation. All right? And I'm going to say, let's assume that every one of those mutations, wherever it occurred, we're just going to assume every one of them gave you a crack at a new 300, a new gene. 300 nucleotide sequence. Every one of them. Of course, that's not going to be true because they're going to be occurring all over the place. But let's assume that. You still only have 1 out of 330, and the assumption in the calculation is that every mutation gives you a chance for a new 300 nucleotide gene. Okay, so that's why I said it's a generous assumption. But under that assumption, you still wind up with only 10 to the 40th rolls of the dice, and then you're left with only 1 out of 10 to the 25th. Okay, so it's a huge problem. Now people say, well, like Shapiro says, I think the cell has a way of constructing new genes as it needs them. Okay, well, that may be, but then the question is, where did the programming come from? Where is the programming to do that? Okay, so it's a huge problem here. Now, in addition to the improbability of randomly generating the new proteins that are necessary for a different body plan, so that's one problem. And it seems like a massive problem. The new body plan, it has to unfold from a single cell after fertilization pursuant to a precisely coordinated process which requires the production of the right proteins, the right building materials and construction signals at the right time. I mean, even I, as ignorant as I am about all things construction, even I know that something as simple as a house, that there's an order and a process that must be followed in building a house if you want to end up with a house. There's an order and a process to it. If the construction doesn't proceed in orderly steps, each one depending on and building on the earlier one, like the foundation, the framing, the electrical, the plumbing, the drywall, the cabinets, there is an order there. If you don't follow that order, well, the house isn't going to get built. And the same is true when you're going to build an organism from that first fertilized cell. There is a plan and a process that must be developed. And in building higher level organisms from that first cell, in doing that, the construction project, it's coordinated in significant part by the timing and the production of specialized proteins, by what are called developmental genes. Now, these specialized proteins, they turn on and turn off other genes as necessary in the unfolding process. So as this cell begins to multiply, divide, differentiate, you have these developmental genes that are turning on and turning off other genes that are needed at the time they're needed in this unfolding developmental process. And these developmental genes, they interact with one another. They have feedback mechanisms that influence their operation, and therefore they constitute what is known as developmental gene regulatory networks. It's as if it's like the developmental genes play the genome in a developing organism like a piano is being played in a magnificent piece of music. They are turning on and turning off. They are orchestrating the unfolding of this thing. And it's just insanely complicated. Meyer says, I don't want to turn around here, I'll just read it from here. Meyer says, developmental biologists have also discovered that building an animal does not just require new genes and proteins, but instead it requires integrated networks of genes and proteins called developmental gene regulatory networks. These networks of genes and their protein products regulate the timing of gene expression as animals develop. The products of the genes in these integrated networks transmit signals that influence the way individual cells develop and differentiate during this process. These signaling molecules influence each other to form circuits or networks of coordinated interaction, much like integrated circuits on a circuit board. For example, exactly when a signaling molecule gets transmitted often depends upon when a signal from another molecule is received, which in turn affects the transmission of still others, all of which are coordinated and integrated to perform specific time-critical functions. Do you see the sophistication of what is going on in going from this cell and this development into this full organism? Now, since developmental gene regulatory networks, since that orchestrates the construction of an organism from that first fertilized cell, to change from one organismal body plan to another would require changing the developmental gene regulatory network. You would have to change the developmental program. In other words, in transforming a body plan of, say, a sponge into a flatworm, having genes that code for the construction of all the building materials necessary for a worm, that wouldn't get you a worm if the developmental gene regulatory network was orchestrating the construction of a sponge. You see, I can have all the materials, but if the programming is orchestrating the construction of a sponge, turning on things in this unfolding process, and I haven't changed that, it doesn't matter that I have all the materials. So you're going to have to change. You're going to have to rewire or reprogram the developmental gene regulatory network. And the process that they would have, it would have to be random. I would have to do this randomly, and the problem is that the experimental evidence, whether you've done it on a zebrafish, whether you've done it on a fruit fly, whether you've done it on a worm, the experimental evidence shows that developmental genes and developmental gene regulatory networks are highly resistant to change. They are highly resistant to change. If you mess with them, the organism dies. Now, Paul Nelson has a PhD in the philosophy of biology. from the University of Chicago, and he specializes in evolutionary theory and developmental biology. And he summarizes in 3 premises the challenge that animal development proposes to naturalistic evolution. He says, 1, animal body plans are built in each generation by a stepwise process, where you have something that's done and then something that's done that relies on that and builds on that. From the fertilized egg to the many cells of the adult, the earliest stages in this process determine what follows. They lock in, they fix what follows, because what follows is built on the earliest steps. He says, thus to morph, to transform, to evolve any body plan, mutations expressed early in development must occur, must be viable, and must be stably transmitted to offspring. 3, such early acting mutations of global effect on animal development, however, are those least likely to be tolerated by the embryo, and in fact never have been tolerated in any animals that developmental biologists have studied. Now, this isn't just Paul Nelson saying this. This is acknowledged by developmental biologist Wallace Arthur. He summarizes the evidence from a wide range of animal systems in his book that was published called The Origin of Animal Body Plan, that was published by Cambridge University Press. He says these genes that control key early developmental processes are involved in the establishment of the basic body plan. Mutations in those genes will usually be extremely disadvantageous. And it's conceivable that they are always so. That's his emphasis, that they are always so. In fact, the only exception to this rule is mutations from a loss of structure. For example, you have cases where if you're developing, you mess with this and the flying beetle loses its wings. All right, well, you can think of some case where that would be advantageous if he's on an island where flying gets him blown into the ocean. All right, but evolution requires the production of new structures, not the loss of structures. So don't be taken in by that. Let me show you 2 slides I took from Paul Nelson, and because he's talking about this, he says this only makes sense. Right here in Drosophila, you say a mutation expressed late in development may affect only a relatively small number of cells. You see, this represents the developmental cascade. As you begin from here, well, if it's being expressed late in development, you can see how it can just affect a few cells. But if you're going to start tinkering way up here, he says mutations expressed early in development, by contrast, are likely to crash the system because of pleiotropy and other downstream consequences. Pleiotropy is the expression of multiple traits by a single gene. All right, so if you start tinkering way up here in the very early basic thing, the likelihood you're going to just crash and destroy the thing are very high. And that's what has been found in laboratories when you go in and start tinkering with those things. Eric Davidson of Caltech, Eric Davidson was the leading investigator of developmental gene regulatory networks in the world. He died some years ago, I think 2015. But he discovered that these networks can't be changed significantly. Stephen Meyer says Davidson discovered that mutations affecting the developmental gene regulatory networks that regulate body plan development inevitably lead to catastrophic loss of the body part or loss of viability altogether. Davidson himself says there's always an observable consequence if a developmental gene regulatory network subcircuit is interrupted. Since these consequences are always catastrophically bad, flexibility is minimal. And this is somebody who's one of the foremost, or was the foremost expert on the subject in the world. Now, given this intolerance of developmental gene regulatory networks to mutation, no one knows how a new body plan could ever evolve. Davidson says, contrary to classic evolution theory, the processes that drive the small changes observed as species diverge cannot be taken as models for the evolution of the body plans of animals. You see, we're going to have to radically alter body plans. And that's going to require not only creating genes necessary to produce the new proteins necessary for those new bodies, but you're also going to have to change the developmental program, and we find that you can't do that. When you go and stick your finger up in here in the developmental program, you destroy the development. And the result then is death. Well, what do people say about that? Well, some, like the evolutionary biologist Charles Marshall, they recognize this, and they say, well, what probably happened is that long time ago, millions of years ago, developmental gene regulatory networks were more amenable to mutation. In other words, they were more flexible back then. Well, as Davidson says, if that's the case, they look nothing like anything we have access to. Because all the developmental gene regulatory networks we can study don't sound like that. But that's the kind of thing that happens, and people wind up saying. Now, last thing I want to say. So you have this idea of the difficulty of producing the necessary proteins. You have the difficulty of altering the developmental program, which has to be done if you're going to change body plans. Finally, in addition to those things, there's the problem of changing the non-genetic or epigenetic, which means beyond genes. The epigenetic contributors to the development of a body plan. Now, as important as DNA is for production of proteins, the proteins that are necessary for countless purposes, all right, countless purposes, all kinds of significance there, the DNA cannot by itself generate a new body plan. It can't by itself. Stephen Meyer, he says, DNA does not by itself direct how individual proteins are assembled into these larger systems or structures. Cell types, tissues, organs, and body plans during animal development. Instead, the three-dimensional structure or spatial architecture of embryonic cells plays important roles in determining body plan formation during embryogenesis, when the embryo is developing. So there's this factor from this spatial architecture of the cells themselves that are influencing the body plan. Developmental biologists have determined several sources of epigenetic, meaning beyond genes, information in these cells. For example, body plan development from an embryo that is influenced by the shape and the location of what's called the cytoskeleton. These microtubules within embryonic cells that serve to help distribute to specific locations essential proteins used during development. And you have different kinds of embryos have different precise microtubule arrangements emanating from an organelle called the centrosome. And they're emanating from that, and those arrangements are not determined by DNA. So there is a non-genetic factor, and that influences body plan development. So if you're going to change from one body plan to another, you're going to have to also change those epigenetic factors that influence body structure, body architecture. And you're going to have to do it randomly, and you say, well, so what? Why don't we do it randomly? Well, because those things aren't subject to the same things that wind up causing mutations of DNA, chemical things, radiation, all that kind of stuff. That doesn't change that. And besides that, because these things are so fundamental and occur so early in the developmental cascade, if you change those, then we're right back to the problem with the developmental gene regulatory network. How are you going to randomly change that structure that influences the body and not destroy the organism? So you have what seem to be very, very large problems. And you say, well, okay, I see that. I hear you talking, but I know there are brilliant people who are down for the struggle. There are brilliant people who are committed to this and say this is in fact, and you're crazy to think that there's any difficulty with it or that kind of thing. Well, maybe they wouldn't say that. But that the idea that there is a mind or a creator, they just poo-poo that idea. Now, what's behind that? Well, to a significant extent, what's behind it, when you're looking at the scientific establishment's view of how life arose or how life diversified, it's helpful to recognize that it's dominated by a philosophical commitment. There is a philosophical commitment to exclusively naturalistic explanations. In other words, they define the discipline of science as a search for only naturalistic, unintelligent causes of the phenomena of nature. That's the way the game is structured. Even when indications of intelligent involvement are staring them in the face, it's an inference that they define as off limits. That is off limits. That is not how science is done. We deal exclusively with materialistic, naturalistic causes and inferring a mind or a intelligent cause. That's a penalty. They say, I don't believe that. Well, let me give you some examples of some people. Richard Lewontin, who was a biologist at Harvard, famously said, in a reviewable book in the New Yorker, I think, he said, our willingness to accept scientific claims that are against common sense is the key to an understanding of the real struggle between science and the supernatural. We take the side of science in spite of the patent absurdity of some of its constructs, in spite of its failure to fulfill many of its extravagant promises of health and life, in spite of the tolerance of the scientific community for unsubstantiated just-so stories, because we have a prior commitment, a commitment to materialism. It's not that the methods and institutions of science somehow compel us to accept a material explanation of the phenomenal world. But on the contrary, we're forced by our a priori, first in advance, our a priori adherence to material causes to create an apparatus of investigation and a set of concepts that produce material explanations, no matter how counterintuitive, no matter how mystifying to the uninitiated. Moreover, that materialism is absolute, for we cannot allow a divine foot in the door. So this is the way it is defined. So I'm not looking for any of that. That's not the game I'm playing. I'm playing a game that is either philosophical naturalism or methodological naturalism, or I'm simply saying I'm looking for unintelligent, blind causes. And that's all I'm looking for. So you say, well, what about all these problems that this Bible guy is talking about? What about those things? I'll say, well, those are matters for research. Right? We're still digging. We're just, okay, I see that, but we're still looking for the processes that will explain this. And we're being well funded to do it. We're still looking for the processes. Now, National Academy of Sciences. I'm through here, but they said statements of science must invoke only natural things and processes. The theory of evolution is one of those. Must invoke. If it doesn't invoke only natural things and processes, then it's not science. And here's Scott Todd, wrote in 1999 in Nature. It says, even if all the data point to an intelligent designer, such a hypothesis is excluded from science because it's not naturalistic. Just this last week, the Journal of Theoretical Biology published a paper, peer-reviewed, published a paper, and then they say they learned, even though the paper uses the word design all through it, cites all kinds of intelligent design theorists. They published the paper, and then they say, well, we've discovered that these people are, what is their phrase that they use? That they are related to creationists. That they're connected to them. Let me see, what do they say here? They are, quote, connected to a creationist group. Now, the one guy here, one fellow was a biologist from Norway. The other fellow was a mathematician from Sweden. And so they've issued a disclaimer from their own publication. And they're being pressured to retract the article. And I've seen that before. You remember the movie Expelled, where Richard Sternberg's stuff, he got fired from Smithsonian. But that's how the game is played. And that's a philosophical thing. All right, as I say, many of you will be happy to know I just wanted to do this because I think it's important that we understand something, that when you say, well, I first have to get you to accept the Bible as true before you will even contemplate theism. I wanted you to see that's not true. Okay? I believe the Bible's true. But I know that in dealing with people who don't, some of us feel paralyzed because I got to get them to accept the Bible is true before I can talk to them. No. You don't have to do that. But the Bible is true. Next. Yes. What Bible verse am I in? I'm not in a Bible verse. I'm trying to help people understand in the idea of trying to be ready to make a defense. I'm trying to help people understand that you don't have to start with the Bible being true. I believe the Bible's true. But I'm trying to help people understand that there's evidence for the existence of God apart from the Bible being true. So, the good news for you is this is my last class in this course. So this is the last one. We'll move on from that. But